Hello everyone. So till now we have studied about what spherical lenses actually are, and we have seen some basic properties, basic principles of these spherical lenses. We have also studied about the behavior of some special light rays when they refract from these spherical lenses. We have also seen the ray diagrams of these special light rays, right? Now we will use all the basic principles and all the concepts that we have studied about to study or to learn about the various cases of image formation with spherical lenses. So we'll start off with learning about the image formation cases with a convex lens. So now the first thing that we'll do is we'll take a convex lens and we'll learn how we draw a ray diagram for this convex lens, right? So we have taken a convex lens and we'll mark the basic points on this convex lens, on this ray diagram, right? So we'll mark the principal axis of the convex lens, the optical center of the convex lens, and both the focus of the convex lens, right? F1 and F2. Now for the purpose of studying image formations, we'll mark two other points on this ray diagram, which basically help us go through the various image formation cases. So these points are 2F1 and 2F2. So now the point 2F1 is basically just a point which is at a distance of 2F, where F is the focal length of the lens. So this point is at a distance of 2F from the optical center of the convex lens. Similarly, the point 2F2 is at a distance of 2F from the optical center of the convex lens on the right hand side of the convex lens. So these are 2 points that will help us understand the various cases of image formations that we'll talk about. So now let's move on to the first case of image formation with a convex lens. So in this case, we will keep the object as far away from the convex lens as possible, right? So we'll keep the object so far away from the convex lens that we'll say that the object is at infinity with respect to the convex lens. So here we are not able to see the object, right? Because it is very far away from the convex lens. Now since the object is very far away from the convex lens, we can safely assume, we can safely consider that all the light rays that are coming towards this convex lens from that object are parallel to each other, right? Even if these light rays are originating from the same point on the object. So if we have two light rays which are originating from a point A on the object, from a point A somewhere on the object, those two light rays, when they are traveling towards this convex lens, we can say that those two light rays are traveling parallel to each other. So now let us try and understand how the image of that object which is placed at infinity with respect to the convex lens will be formed by this convex lens. So now what we'll do here is, we'll take two special rays which are traveling from the point A on the object and which are traveling towards the convex lens. Now using these two special rays, since we know the behavior of these rays, we'll be able to see how they refract after the convex lens, right? And what their behavior will be. So here we'll take some point A on the object and we'll take two special rays which are coming from this point on the object. So let's take the first special ray which is traveling parallel to the principal axis of this convex lens. So the first ray that we've taken from point A is traveling parallel to the principal axis of this convex lens. Now the second light ray that we'll take from the point A, let's again take a ray which is traveling parallel to the principal axis of this convex lens. Now this is possible since the object is so far away from the convex lens that we can assume, or we can safely consider, that two light rays which are coming from the same point can come towards the convex lens parallel to each other. So now here we have taken two different rays, both special rays which are traveling parallel to the principal axis of the convex lens, and we have taken these two rays on either sides of the principal axis. Now we know that any ray which is traveling parallel to the principal axis of a convex lens, after refraction through the convex lens, moves in such a way or refracts in such a way that it passes through the focus of the convex lens. So now these two rays which are traveling parallel to the principal axis of this convex lens, after refraction from the convex lens, they refract in such a way that both of them, they move towards the focus of the convex lens and they pass through the focus of the convex lens. So now here we can see that the two refracted rays, right? The two refracted rays that we have, they both intersect, they both meet at a point which is the focus of this convex lens, right? So both these rays, both these refracted rays which are coming from the point A on the object, they meet at the focus of this convex lens. Now this is the point where an image of the point A on the object is formed by this convex lens. So any point where two refracted rays meet after refraction from the lens, where these two rays are coming from the same point on the object, that is the point where an image of that point on the object is formed by the spherical mirror. So in this case, that point where the two refracted rays meet after refraction is the focus of the convex lens. So here we can say that the image of that point A on the object is formed by this convex lens. Now if we repeat the same practice for all the points on the object, we will find the image of the actual object, right? Because we'll find the image of all the points on the object, and that will recreate the object in the form of an image by this convex lens. So here, if we repeat this practice for all the points on the object, we will find that all the points, they lie on the focus of this convex lens, which means that a point image of the object which was placed at infinity with respect to the convex lens is formed at the focus of this convex lens after refraction. So a convex lens for an object placed at infinity with respect to the convex lens forms a point image of that object at the focus of the convex lens. So now if we try to summarize the position and nature of the image that is formed in this case, where an object is placed at infinity with respect to a convex lens, we can say that the image for such an object is formed at the focus of the convex lens. About the nature of the image, we can say that since their refracted rays actually meet to create the image of the object, the image that is formed by the convex lens in this scenario is actually a real and inverted image. Now we can also see that the convex lens forms a point image or a highly diminished image of the actual object, right? So if we compare the size of the image to the size of the object, we can say that the size of the image in this case is highly diminished when compared to the size of the object. So in this case, where an object is placed at infinity with respect to the convex lens, a point size image, a real and inverted point size image, highly diminished image, is formed at the focus of the convex lens by the convex lens. So this is the first case of image formation with a convex lens, where the object was placed at infinity with respect to the convex lens. So now in this whole scenario, you have seen that we have just used the basic principles to form the ray diagram of this image formation case, right? So you can memorize these image formation cases as well, but if you cannot memorize these cases, it is not a problem, because we can easily form these ray diagrams by just using the basic principles that we have studied throughout this chapter. And using those special rays and the behavior of those special rays, we can easily recreate a ray diagram of any image formation scenario, and we can predict the position and the nature of the image using the same basic principles. So now let's move on to the second case of image formation with a convex lens. So now in this case, what we will do is, we'll move the object a little closer to the convex lens. So here in this case, we'll keep the object, or we'll position the object in such a way that it is placed between 2f1 and infinity. So the object is placed in front of the convex lens in such a way that it is placed between 2f1 and infinity, or beyond 2f1. So now we have the position of the object with respect to the convex lens. Now we can do the same practice again, we can repeat the same procedure again, and we can predict the position and the image and the nature of the image that is formed by this convex lens. So here we'll again take two light rays, all coming from the topmost point of this object, which we have labeled here as A, and we'll take two special light rays and we'll first see the behavior of these two light rays, and we'll form the image of this point A on the object. If we are able to form the image of point A on the object, we can repeat that practice for all the points on the object, and that will give us the image of the object, right? So here again we'll take two rays and we'll see how these two rays behave when they refract by this convex lens. So the first ray that we'll take, which is traveling from the point A towards this convex lens, we'll take this ray to be parallel to the principal axis of this convex lens. Now we are all aware that such a ray, after refraction from the convex lens, moves in such a way that it passes through the focus of the convex lens. So here we have taken the first light ray and we see that this light ray, after refraction from the convex lens, passes through the focus of the convex lens. Now we'll take the second special light ray. So the second special light ray that we'll take in this case is a light ray which is traveling towards the optical center of this convex lens. So we have studied in our previous lectures, right, that any ray which is traveling towards the optical center of a convex lens passes through the convex lens without showing any deviation or any refraction at all. So here we know the behavior of the second special ray as well. So this second special ray that is traveling from the point A on the object towards this convex lens is traveling in a manner that it is traveling towards the optical center or through the optical center of this convex lens. So here we see that this particular light ray travels through the convex lens without showing any deviation. So now here we can see that both these light rays, the first light ray and the second light ray, after refraction from the convex lens, after passing through the convex lens, they meet at a point A dash, and this point A dash horizontally lies between f2 and 2f2 of this convex lens, right? So horizontally, if we try to measure where this point lies, we can say that this point lies between f2 and 2f2 of this convex lens. We can also see that this point lies beneath or below the principal axis of the convex lens. Now if we repeat this same process for all the points on this object, we'll be able to recreate the image of this object. So here we can see that an image A dash B dash of the object AB has been recreated by this convex lens. Now here we can clearly see that the image that is formed is again formed by the meeting of refracted rays from the convex lens, right? By the actual meeting of these refracted rays. So the image that is formed is real and inverted in nature. The position of this image lies between the f2, between the point f2 and 2f2 of this convex lens. We can also see that the image that is formed is diminished in nature if compared in size with the actual object. So if we compare the size of the image and the object, we can see that the size of the image is actually smaller when compared to the size of the object. So we can say that the image that is formed is actually diminished in nature. So now we can summarize this case of image formation, right? We have drawn the complete ray diagram and now we can summarize this case. So the position of the image for an object placed beyond 2f1 or between 2f1 and infinity in front of a convex lens, the position of the image is formed between f2 and 2f2 of the convex lens. We can also see that the nature of the image that is formed is actually real and inverted, and it is diminished in size if compared to the size of the original object. So this is the second case of image formation with a convex lens. Now if we move to the third case of image formation with a convex lens, we will again move the object a little closer to the convex lens. So now we'll move the object a little more closer to the convex lens and we'll place the object, we'll position the object so that the object stands directly above the point 2f1 of the convex lens, right? So the object is at point 2f1 with respect to this convex lens. Now we have the position of the object with respect to the convex lens. So now you can follow the same practice and we can again predict the position and the nature of the image that is formed in this particular case. Go ahead and give it a try. Try to draw the ray diagram again of this particular case using the same principles, using the same steps, same process that we have followed in the first two cases, and see if you can predict the position and the nature of the image. Well, I'm sure almost all of you must have been able to do that. So let us go ahead and try and understand what happens in this particular case. So in this case, we can see, so we'll again take the topmost point of the object and we have labeled it here as A. Now we'll again take two special rays which are coming from this point on the object and which are traveling towards the convex lens. Now from these two special rays, we'll predict how these special rays behave after refraction from the convex lens, because we are aware how these two rays behave with the convex lens. So the first special ray that we will take is again a ray which is traveling parallel to the principal axis of this convex lens. Now we know that this ray, after refraction from the lens, is going to pass through the focus of the convex lens. So here we have drawn the first light ray which is traveling parallel to the principal axis of the convex lens, and after refraction passes through the focus of the convex lens. Now the second ray that we'll take is, the second special ray that we'll take is again a ray which is travelling in such a way that is travelling towards the optical center of the convex lens. Now we know that this ray is going to pass through the convex lens without showing any deviation. So here we have drawn the second ray, second special light ray, and we see that this passes through the optical center of the convex lens and it passes through the convex lens without showing any deviation. So now in this case we can see that these two rays, these two refracted rays, the first ray and the second ray, they refract from the convex lens, and after refraction they meet at a point A dash which directly lies below the point 2F2. So if we measure this, the position of this particular point A dash horizontally, we'll find that this point lies at an exact distance of 2F from the convex lens, from the optical center of the convex lens, but it lies below the principal axis. So this point A dash lies directly below the point 2F2 of this convex lens. Now if we repeat this same practice for all the points on the object, we'll be able to draw the image of the object, right? So doing that, we can see that the image of the object AB is obtained as A dash B dash, and we can see that this image is positioned at the point 2F2 of the convex lens. So in this particular case where we place the object at the point 2F1 with respect to the convex lens, a real and inverted image of that particular object is formed at the point 2F2 or at an equal distance from the convex lens, in this particular case by the convex lens. Now about the size of the image, if you try to measure the size of this image, you will find that the size of this image is exactly same as the size of the object. So in this case, the image that we have obtained is of an equal size to the size of the actual object. So if we try to summarize this particular image formation case, the position of the object with respect to the convex lens was that the object was placed at the point 2F1 with respect to the convex lens. Now the image is formed at the point 2F2 with respect to the convex lens or at an equal distance from the convex lens as the object was placed from the convex lens. The image that we have obtained is real and inverted in nature and is of the exact same size as that of the object. So this is the third case of image formation that we have seen with a convex lens, where we had placed the object at 2F1 of the convex lens. So till now we have seen three different cases of image formation with a convex lens, right? If we observe all these cases together, we'll be able to find certain patterns in the position, in the respective position of the image with the object and the relative size of the image with respect to the object. And these relations or these trends, these patterns help us understand the behavior of a convex lens better. So let us go through these patterns one by one and understand how these patterns actually take place. So let's talk about the relative position of the image with respect to that of the object in all the three cases of image formation that we have studied. So if we take all the three cases, we can see that when the object was placed at infinity with respect to the convex lens, an image was formed, a point image was formed at the focus of the convex lens. In the next case, when we moved the object a little closer towards the convex lens, we saw that the image started to move away from the convex lens, right? In the second case, where we had placed the object somewhere between 2F1 and infinity, we got the image to position between the focus, which is F2, and 2F2 of the convex lens. As we move the object even closer, when we place the object at 2F1, we could observe that the image also moved away from the convex lens and it got placed at 2F2. So this shows a pattern in the relative position of the image with respect to that of the object. So as we move the object closer towards the convex lens, we can observe that the image also moves away from the convex lens. So this is a trend, this is a pattern which is in general true, and with convex lens, for all the cases of image formation with a convex lens, this rule or this general pattern is followed. So as we move the object closer to the convex lens, we will find that the image moves farther away from the convex lens. Now a similar trend can also be observed in the relative size of the image with respect to that of the object. So in the first case, we can see that when the object was at infinity with respect to the convex lens, a point-sized image or a highly diminished image of the object was formed at the focus of the convex lens. As we moved the object closer to the convex lens, we could see that the size of the image started to increase. Right? As we move the object even closer to the convex lens and we place the object at 2f1 with respect to the convex lens, we could see that the image was of the exact same size as the object. So as we move the object closer to the convex lens, we can see that the size of the image that is formed keeps on increasing. So this is another pattern which in general is true with image formation cases of convex lens. So for all the further cases that we'll study about, you'll observe that this pattern still stands true. So these two patterns give us a little more insight into the behavior of these convex lenses, and it tells us how these convex lenses forms images of various objects which are placed in front of the convex lens at various different positions. So now let us move on to the fourth case of image formation with a convex lens. So now in this case, we'll move the object even closer to the convex lens and we'll place the object between f1 and 2f1 of the convex lens. So we'll place the object somewhere between f1 and 2f1, the points f1 and 2f1 with respect to the convex lens. So now again we'll follow the same practice. Go ahead and give it a try. Try to find the image, the position and the nature of the image when the object is placed between f1 and 2f1 of the convex lens. So we'll follow the same practice again, right? We'll take two special rays and we'll see how these special rays behave, and we'll find the image of the topmost point of the object, which we have labeled here as A. So again, the two special rays that we'll take are the two rays, which the first ray is the ray which is traveling parallel to the principal axis of the convex lens, which after refraction passes through the focus of the convex lens. And the second ray that we have taken is the ray which passes through the optical center of the convex lens, which passes through the convex lens without showing any deviation. So now here we can see that both these two rays, after refraction, they meet at a point A dash, which horizontally lies somewhere beyond the point 2f2, right? So this point horizontally lies between 2f2 and infinity. So now in this case, again we'll follow the same practice for all the points that are there on the object so that we can recreate the image of the object. So here if we do this for all the points on the object, we can see that an image A dash B dash of the object has been formed beyond the point 2f2 or between 2f2 and infinity of the convex lens. So the object that we had placed was at the position of between f1 and 2f1 of this convex lens. So here we have the position of the image. Now we can see that a real and inverted image of the object is formed, and also that the image is enlarged in size when compared to the size of the original object. So if we try to summarize this particular image formation case, we can say that when an object is placed between f1 and 2f1 of a convex lens, the image of that object is formed at the position of beyond f2 or beyond 2f2 or between 2f2 and infinity of the convex lens. We have also seen that a real and inverted image is formed in this case, which is actually enlarged in size or more in size when compared to the size of the original object. So this is the fourth case of image formation with a convex lens. Now let us move on to the fifth case of image formation with a convex lens. Now in this case, what we'll do is we'll move the object still closer to the convex lens. So in this case, we'll keep the object at f1 with respect to the convex lens. So we have kept the object at the focus of the convex lens. So now we have the position of the object with respect to the convex lens. Now again go ahead, give it a try. Try to draw the ray diagram that represents the image formation in this particular scenario. So it's the repeat of the same practice. We'll again take two special rays and we'll see the behavior of these two special rays. So here we'll take the first ray, which is traveling parallel to the principal axis of this convex lens. And the second ray that we'll take is a ray which is traveling in the direction of the optical center of this convex lens. But in this case, what we observe is that after refraction from the convex lens, both these rays, they start to travel parallel to each other, right? So the first ray, it passes through the focus of the convex lens, and the second ray passes through the optical center without showing any deviation. what we find is both these refracted rays are actually parallel to each other. So in this case, we cannot find a point where these two rays are meeting together. So in this case, we say that both these rays which are traveling parallel to each other are going to meet at infinity, which means that an image of this point A on the object is going to form at infinity with respect to this convex lens. So in this case, if we repeat this practice for all the points on the object, we can see that all the rays after refraction become parallel to each other, and thus we can say an image of this object is formed at infinity with respect to the convex lens. So in this case, where we had placed the object at the focus of the convex lens, we find that a real and inverted image is formed at infinity with respect to the convex lens. In this case, what you observe is that the image that is formed is highly enlarged in size when we compare it to the size of the original object. So in this particular case of image formation, where the object was placed at the focus of the convex lens, an image, a real and inverted image of that object was formed at infinity with respect to the convex lens. And the image that was formed was highly enlarged in size, or was much higher in size when compared to the size of the original object. So this is the fifth case of image formation with a convex lens. Now let's move on to the sixth case of image formation with a convex lens. Now in this case, what we'll do is we'll move the object still closer to the convex lens. So in this case, we'll move the object and we'll place the object between the optical center of the convex lens and the focus of the convex lens, right? So here we have placed the object between O and F1. Again, we'll repeat the same practice, right? Again, we'll take two special rays and we'll see how these two special rays behave after refraction from the convex lens. So the first ray that we take travels parallel to the principal axis of the convex lens, and after refraction through the convex lens passes through the focus of the convex lens. Now the second ray passes through the optical center of the convex lens, and thus after refraction passes undeviated through the convex lens. Now in this case, what we observe is that both the rays after refraction are actually diverging. So we know that two diverging rays are never going to meet each other, right? So these two rays after refraction start to diverge. So we cannot say where these two rays are going to meet. So what happens in this case? Is there no image formation in this case? Well, in this case, what happens is if we observe this whole phenomena from this particular position, we'll see two diverging rays coming towards us, right? Now, how we will perceive these two rays is that we will feel or we'll perceive these two rays, these two diverging rays that are coming towards us, to be coming from some point which is behind these two rays, right? So if we extend the path of these two rays backwards, we can see that these two paths, they meet at some point A dash behind the two rays, behind the convex lens. Now, if we observe this whole phenomena from the position that we are in, we will feel that these two diverging rays are coming towards us from a point, right? And these two rays are actually coming from the point A dash. So our brain will perceive these two rays as if they are coming from this point A dash behind the convex lens. So in this case, we say that these two rays, they appear to meet at the point A dash behind the convex lens. So an image of the point A appears to have been formed at the point A dash beyond the convex lens. So in this case, we say that a virtual image of the point A on the object is formed at the point A dash by this convex lens. Now if we repeat the same practice for all the points on the object, we'll be able to create a virtual image A dash B dash which lies behind or beyond the convex lens, right? So now this image that has formed A dash B dash of the object AB is actually a virtual and erect image, because this image is not formed by the meeting of two refracted rays, right? It appears that this image has been formed of this particular object. So that is why we say that this image A dash B dash is actually a virtual and erect image of the object AB, which is placed between the optical center and the focus of the convex lens. So now in this case of image formation, the position of the image is behind the convex lens, right? And we can see that virtual and erect image of the object has been formed. We can also see that the image that is formed is actually enlarged when compared to the size of the original object. So the image that is formed in this case is higher in size when we compare it to the size of the actual object. So this is the sixth case of image formation with a convex lens, where we place an object between the optical center of the lens and the focus of the lens, and we find that a virtual and erect image is formed behind the convex lens, and the image that is formed is actually enlarged in size or higher in size. So these are all the 6 cases of image formation with a convex lens that we have studied about in this chapter. Now, all these 6 cases, the ray diagrams for all these 6 cases, we could easily draw all these ray diagrams by just using the basic principles and the basic concepts about spherical lenses and the behavior of some special rays that we have studied about. So these are all the cases of image formation with a convex lens and all the concepts related to the image formation of a convex lens. Now in the next lecture, we'll study about the image formation cases with the help of a concave lens. Later on in the chapter, we'll study about the numerical aspects of these image formation cases, and we'll see how we solve problems based on these concepts. See you in the next lecture.